So last time we talked about linear equations, and we saw at the end when we were putting things into parametric form that if you only have one linear equation and you have more than one unknown, there are going to be infinitely many solutions. That was sort of a reading between the lines takeaway. So the natural question is, can we put more constraints on it so that there might be a unique solution? And this leads us to the idea of systems of linear equations, or simultaneous equations. Equations which, say we have n unknowns, or 3 unknowns say, and we want it to solve 2 different equations. Can we do that? And how do we solve such equations? So now I'm going to throw you right into the thick of things. This is our general system of m equations in n unknowns. Notice that m and n are not necessarily the same. You may have more equations than unknowns, less equations than unknowns, or the same amount. And essentially, so if you just zoom in on one of these equations, let's just look at the top one, notice it's the same thing as last time. It's just a linear equation in 1, 2, 3, all the way up to n different variables, right? We have our coefficients, we have our n x's, our indeterminates, we have our constant over there, and we talked about that last time. But here we have another one satisfied by the same x1, x2, x3, all the way up to xn, and so on. And we have, in general, m equations, and you see here, 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 etc. We have n unknowns. And for this reason, m equations that are satisfied by n unknowns, we in general would call this an m by n system of linear equations. You'll often also see me write SLE for system of linear equations. So the question is, can we find values x1, x2, all the way up to xn, that n tuple we talked about before, that satisfies not just this equation, because we said oftentimes there will be infinitely many solutions to one equation. So what if we were to pair 2 equations together and say, well, take one of the solutions which satisfies this one, is there one which also satisfies this one, the same x's? And we'll see when that's the case. It's going to depend on what m is, what n is, and what all these coefficients are. And just as before, our notion of a solution to this is going to be an n tuple, y1, y2, all the way up to yn, such that if we set xi equal to y sub I for all I, so y1 equals x1, y2 equals x2, etc. If we plug in these y values for the x's, then it satisfies, what we get is a true statement for each of these m equations. That would be considered a solution to our system of linear equations. Let's do a quick example just so you can concretely see what a solution means. So we have 2x minus 3y equals 10, and we're going to say x and y have to satisfy that in addition to the second equation, which says that x plus 2y equals 9. Together, these constitute our system of linear equations. 2 equations, so m equals 2, in 2 unknowns, so n also equals 2 here. And having designed this problem, I know the answer. We're not worried about solution techniques right now, only what a solution means. So if I were to set x equal to 1 and y equal to 4, let's show that this does indeed solve the pair of equations. So 2 times x, which is 1, minus 3 times y, which is 4. Well, this is 2 minus 12. Oh, this is supposed to be negative 10, my bad. Is equal to negative 10. And the first one is satisfied. Okay, now the second equation, x, which is 1, plus 2 times y, which is 4, is equal to 1 plus 8, which is 9. And we see that this pair, x and y, do satisfy both equations at the same time. This is what it means to have a solution to our system, right? And we can write it as an ordered pair 1, 4. Now let's talk about consistency. What does it mean for a system of linear equations to be consistent? Well, it just means that they have at least one solution. Could be more than one solution still, just as we saw in the case of one linear equation. With a system, we can also have more than one solution, and in which case it would be a consistent system. However, it would be inconsistent if there is not any solution which satisfies all the equations. For instance, 2x plus y is equal to 10, and 2x plus y is equal to 9. These are incompatible, you should see, because 2x plus y, what's on the left and both sides, can only have one value for each given x and y, right? So that if 2x plus y is equal to 10, it cannot also be equal to 9. So this is an example of an inconsistent system of linear equations. Let's now look at examples of consistent and inconsistent systems and see what conclusions we can draw. So first, let's consider these two lines. 2x plus y is equal to 1, similar to our last example, and 2x plus y is equal to 0. Clearly, this is an inconsistent system, right? You don't have an inconsistent equation. No equation isn't inconsistent on its own, right? But together they're inconsistent. And what do these represent geometrically if we look at the locus of solutions to both of these individually? Well, they represent two parallel lines. And these parallel lines never intersect one another, hence why we do not have a solution of the system. So this is our first example. Second example, let's look at 2x plus y is equal to 1 again. But now, for the second one, let's look at negative 1/2 x plus y is equal to 1. These two equations are actually consistent with one another, and in fact, they look like this if you graph them. They are two lines which intersect, in fact, at a right angle and at exactly one point. And this single point is the only coordinate pair xy which satisfies both of these equations simultaneously. So this solution, so first we had an inconsistent system. Inconsistent. Now we have a consistent system with one solution. All right, now let's look at one more case. Suppose we have 2x plus y equals 1 again, and 6x plus 3y is equal to 3. Now, if you were to graph these two lines, what would you get? Well, there's the first line, and there's the second line. They are, in fact, although you don't immediately see this from looking at them, they're in fact the same line. If you were to look a little closer, you would notice this equation is just 3 times that equation. All right, so this, if you pick any point on the first line, right, any point which satisfies this, it will automatically also satisfy the second equation. So this is a consistent system with infinitely many solutions, because you can pick any point on the line. Infinitely many solutions. So these are 3 cases, and the question is, are there any other cases? Or does this completely summarize systems of linear equations? And the answer is, this completely characterizes them. Every system of linear equations will have exactly either no solutions, exactly one solution, or infinitely many solutions. Last thing I want to talk about this time is a special form of a system of linear equations called row-echelon form. So if we have a system x minus 4y plus 3z is equal to 10 is our first equation, then for the second equation we have y plus 5z is equal to 11, and for the last equation z is equal to 1. Take a look at this, and what do you notice about this system of 3 equations in 3 unknowns? Well, it's going to be very easy to solve. Why? because the last equation already gives us z, so what can we do? We can plug z into the previous equation, then move this number to the other side, then we have y. Then we can plug z into here and y into here, and once again move both numbers to the other side, and we get x. This process is called back substitution, and it is a very easy way to solve a system of linear equations. If it is already in this form, or as we'll see later, if we can coax the system of linear equations into this form, it is really nice. In fact, computers like this kind of form as well, because it's very simple. Not very many flops or floating point operations. So, if whenever you see this stair-step pattern and the coefficients out front of our leading variables in each equation, the first variable is just called the leading variable. Whenever these coefficients are 1 and you see the stair-step pattern, you know the system of linear equations is in row-echelon form. This is going to be important later. Before we go, let's do one example of this back substitution process real quick. So let's look at this equation and first make sure that it's in row-echelon form so that we can do this. Is this in row-echelon form? Well, we have our stair-step pattern and we have 1, 1, but right here we have a 5 as the coefficient. So this is not in row-echelon form and we can't do simple back substitution. However, here, let me change the system of equations. It's a different system now that is in row-echelon form, and let's try solving this. Well, by the third equation, we already know that x3 is equal to 5. So we'll just write that down here. Now, if we plug that into here, we get x2 minus 15 is equal to negative 16. So x2 is going to be equal to negative 1. Let's plug both of those values into here. x2 is negative 1, x3 is 5, and what do we get? We get x1 plus 2 plus 5 is 8. Well, this is 7 together, so x1 must be equal to 1. And so we see how to do back substitution. You plug this value into here, you plug both these values into here, and we can write our final answer as an ordered triple here, as 1, negative 1, 5. Solving a system by back substitution when it's in a row-echelon form.